Question 15 is about the charging circuit for a car battery. So you've got a power supply connected to the terminals of the car battery. So it tells you the EMF of the power supply. It also tells you it's got some internal resistance. It tells you what the EMF of the car battery is to begin with. 10 volts. If you know anything about car batteries, they're supposed to be 12 volts. So that's a sign that this battery is flat and needs charging up. So the first thing you ask for, the total EMF of the circuit when charging begins. So you've got effectively two power supplies in the circuit. You've got the power supply from the charger and you've got the battery. So you've got to find the total EMF. Now the word total is a little bit misleading. So you need to consider which way the two sources are pushing. The power supply is trying to push current around the circuit that way. The car battery is trying to push current around the circuit that way. So when you work out what the total EMF in the circuit is, you have to take that into account. In other words, you don't have them together. Next part, it tells you that you adjust the value of R so that the initial charging current is 0.25 amps. And you've got to calculate the value of R. And even though I've been tackling circuit problems for hundreds of years, I would still genuinely never start doing a question without drawing a sketch of the circuit. Some people seem to think this is extra hard work, but to me it's much harder doing it without drawing a picture, because a picture makes it so much easier to keep track of what's going on. So we're trying to choose the right value of R to give a current of 0.25 amps. So by drawing the circuit, including the internal resistance of the car battery and the internal resistance of the power supply, drawing them as if they were separate little resistors, even though we know that the resistance is really spread through the chemicals or through the wiring inside. By drawing a picture like that, it helps us to keep track of the total resistance. So we know we've got the two batteries pushing against each other. Well, you've already worked out what the resultant EMF is. You can now very easily see what the total resistance is. You've got that and that and that all in series, so they make the total resistance. So if you use the equation V equals IR, you know what V is? V is the total EMF in the circuit, or the resultant EMF. I is the current that you want, 1/4 amp, and R, now let's be careful here, because the R in this equation means the resistance that goes with that voltage, and since that voltage is the total voltage for the circuit, the R that goes in the equation is the total resistance for the circuit. It's not just that thing that's called R, so we've always got to be careful with what we call things. So even though we refer to the equation as V equals IR, we've got to remember that the R that's in the equation might not necessarily be the thing that's labelled as R in our diagram. So the total voltage is current times the total resistance. So we know the voltage, we know the current, we can use that equation to find the total resistance, and we know that the total resistance is made up of this value of R that we adjust in series with those other two internal resistances. So we should be able to work out what R is. And part C is really easy to finish off with. It says it's charging for 8 hours. You've got to calculate the total charge that flows through, assuming that the current remains constant. So as long as you know the relationship between current and charge, and you don't make a silly mistake with the units, remember to convert the 8 hours to the proper units we should be using. That should be a really easy question.